Now let's come to an important topic. Let us say there is a block on a rough surface, that is surface that has friction. There is an object of mass say m sitting on it, and it has been pulled by say P, a force. And as a result, the block displaces from this position through a distance of s, or since it's moving in a straight line, this will also be equal to the displacement. And so the block's final position is this. Okay. Now, when the object moves over the rough surface, that is the surface that offers friction to the movement, relative movement or sliding, a force of friction will apply, right, in the interface in the opposite direction. Let's call this F. Since it's a kinetic friction, we can put the suffix Fk. Now, we already know that if a force is applied on an object and there is a displacement, then some work is done. This force P applied on mass m will displace it from initial position to the final position, and so it will do certain work. This will be a positive work. However, we have in class 9 only we have studied that if the object moves in a direction against the direction of the applied force, as is the case with the force of friction. Force of friction applies this direction, but the object moves in the opposite direction. In such case, work is done, not done by the force, but the work is done against the force. So, that work done is what we are going to study in this topic, work done against friction. So, friction tries to resist the motion, but in spite of that, the object moves. So, how much work needs to be done against the force of friction to move the object? That is our objective to find. To do that, we need to notice that there will be a weight that is acting downwards on the object, and there will be a normal reaction to the weight R, which are equal. R equals to mg but in opposite direction. Now, by definition of work, we know that work done in magnitude is given by the applied force, in this case the force of friction, multiplied by the displacement. However, force of friction is given by coefficient of friction multiplied by normal reaction and then into S. But R equals to mg, so this will be equal to mu k mg into S. That is to say, work done against friction has a magnitude of this. This will be, of course, if we consider the directions, it will be a negative work. Because friction doesn't do work, work is done against the friction. This point needs to be remembered. Okay, now let's consider the next case where instead of having a horizontal plane, the object is now pulled with a force of force of P along an inclined plane in the upward direction, and the object moves up the plane at a constant speed. It's not accelerated. Okay, in this case, what will be the work done against the friction? Okay, to do that, first let's say what are the forces acting on it. The upward pull is there, of course. Then there will be a friction that will oppose along the line connecting these two. So this will be force of friction. Since it's sliding, so it's force of kinetic friction. Then there will be a downward force which is mg, weight of the mass, and then perpendicular to the incline there will be a force which is the normal reaction or the reaction force of the plane. Let's call this R. So, to understand this better, what we need to do is that we need to resolve the mg, which is not along or perpendicular to the plane, into two components. One component perpendicular to the plane and the other component along the plane. So these two will be the components of the force mg. This angle will be theta, so it will be mg cos theta, and this will be mg sin theta. So if we consider now the equations of motion parallel to the plane, along the plane, and perpendicular to the plane. Let's say perpendicular to the plane. If we say perpendicular to the plane, then there are two forces. One is the reaction force, and the other one is the vertical component or perpendicular component of mg, that is mg cos theta. These two must balance each other so that the object doesn't sink into the plane. So R must be equal to mg cos theta. If we consider the horizontal case, then there is an upward pull P, or horizontal in the sense along the parallel to the plane. Parallel to the plane, then what we have? Upward push. Since there is no acceleration, the object is moving with constant speed, then this must be equal to the downward forces of mg sin theta plus Fk. Now we already know that Fk is equal to mu k into r, but from the first equation r is found to be mg cos theta, so this will be equal to mu k mg cos theta, which means the net force, upward force that needs to be done, equals to mg sin theta plus Fk, that is mu k mg cos theta, or we can say mg sin theta plus mu k cos theta. So what will the work done by the force? F must be equal to applied force into displacement, which will be simply substituting the value of P here, we get mg sin of theta plus mu k cos of theta into the displacement. So not F, sorry, this will be the work done. So work done against friction to pull the object up the plane at constant speed will be given by this particular equation. W equal to mg sin theta plus mu k, where mu k is the coefficient of kinetic friction, theta is the angle of inclination of the plane, and s is the displacement. So given by this particular equation. Okay, now let's move on to the next topic, that is when an object moves down an incline, what will be the work done with constant speed. In this case also, we know that there will be two forces that are there. One is that mg acting downwards, and the normal reaction R perpendicular to the plane. If we resolve mg into two components, mg cos theta and mg sin theta, perpendicular to the plane and along the plane respectively, then R must balance mg cos theta. So perpendicular to the plane, this equation R equal to mg cos theta still holds. However, down the plane, now what happens is that the pull will be now down the plane. So the force P will be applied downwards. As a result, a frictional force Fk will now act up the incline. So for the horizontal case, now the net downward force will be P plus mg sin theta and P here, and that must equal the frictional force, so that the object moves with constant speed. There should be no acceleration, so the net force must be 0. So net downward force along the incline must be equal to net upward force along the incline. However, Fk is given by mu r. Fk is mu k into r, but r is mg cos theta from the first equation, so we have Fk equal to mu k into mg cos theta. Therefore, P will be equal to this value mg into mu k cos theta minus sin theta, and so the net work done, W equal to Ps, where S is the displacement of the object down the plane due to the applied force, will be mg into mu k cos theta minus sin theta whole thing multiplied by the displacement s. Okay, now let's consider a case where the incline, the angle theta is such that it is greater than the angle of repose, as we discussed in our previous videos. If you haven't seen them, the link is given in the description below. You may please refer to them. Now what happens is that if the object slides down, if the theta is greater than the angle of repose, then the object will spontaneously slide down the incline. And let's say it slides down with an acceleration of a in the downward direction. So what will be this acceleration, or what will be the value of this acceleration? For this, we again consider the equations of motion along the plane and perpendicular to the plane. Now along the perpendicular to the plane, the normal reaction must balance the perpendicular component of mg, that is mg cos theta. So r equal to mg cos theta. Along the plane, what will happen is that there will be a net force F downwards, which will be equal to the net downward force mg sin theta, the component of the force or weight along the plane, minus the frictional resistance or force of friction, which is equal to mg sin theta. Fk we have already seen in the previous cases also is equal to mu k mg cos theta. But this F is responsible for this acceleration down the incline. So we can rewrite this as m into a, which means that a must be equal to g sin theta minus mu k g cos theta, because m's will cancel out. This m and this m will cancel out. So g sin theta minus mu k g cos theta will be there, or we can say, taking g common, g into mu k, or sin theta into mu k cos theta. This will be our acceleration that will be produced if the object starts moving downwards, slide downwards with an acceleration a under the influence of gravity. Okay. We have been given that a bullet of mass 0.01 kg, 0.01 kg is moving towards a block, and it hits the block with that some velocity v, and gets embedded to the block. The block has a mass of mass equals to 4 kg. The whole system moves for 20 meters before coming to rest. We have to find, coefficient of kinetic friction is given to be equal to 0.25. 25. We have to find the velocity with which the bullet hit the block. To solve this problem, let's visualize this. Let's say there was a bullet moving with an initial velocity. Let's call this u. It's given as v, right? V equal to what initial velocity? We need to find this particular velocity. Let's call the mass of the bullet to be equal to m. Now, next is that there is a block whose mass we will call capital M, and the bullet gets embedded to it. So the whole system will start moving with certain velocity. Let's call this v, capital V. And after traveling certain distance, this system of bullet and the block comes to rest. Let's call this distance s, which is given 20 meter, m is given 4 kg, small m is given to be equal to 0.01 kg, and coefficient of friction between the two surfaces is given, that is the object is standing on a surface. Okay. Now, first thing first, the object was initially at rest. So, when the bullet hits it, it will start moving with certain velocity v. After the bullet hits the block, there is no force in the forward direction. However, force of kinetic friction will be acting along the point of contact between the surfaces in the backwards direction. And this will produce an acceleration in the direction opposite to the direction of motion of the block and the bullet system, which will retard the bullet, and finally after traveling a distance equal to 20 meters, the system comes to rest. So like the previous case, what we need to do first is that we need to find the acceleration produced. To do that, what we will do is that, notice is that the force of kinetic friction will be given by mu k into r, normal reaction. Now what is normal reaction? If we consider the block and the bullet system, the normal reaction will, weight will be m plus small m into g, which will be balanced by the normal reaction. So r will be equal to m plus small m into g. Right? Equals to mu k m plus m into g. Right. However, this particular force of friction, as we said, has produced the acceleration a in the system. So this must be equal to m plus m into the acceleration that is produced, from which we can always solve and find a will be equal to mu k m plus small m into g, whole thing divided by m plus small m, that is equal to mu k into g. Mu k is given 0.25. G, let's for simplicity take it as 10 meter per second square as in the previous case. So we will have an acceleration equal to 2.5 meter per second square in the direction opposite to the direction of motion. Let's note this down somewhere. A is found to be 2.5 meter per second square. Now, if we know this, then using the equation of kinematics, that is this equation, v square minus u square equal to 2as. A we have found, s has been given, the final velocity after traveling this distance has been given to be equal to 0, and u here is equal to this velocity with which the object starts to move. So if we substitute the values, we get 0 minus v square, this v, equal to 2 minus 2.5, because it's a negative acceleration, s is 20, which will give us v square equals to 5 into 20, 100. Therefore, v will be equal to 10 meter per second. So, v equal to 10 meter per second. The velocity with which the system of mass or the block and the bullet starts moving is this 10 meter per second. If it is so, and we have seen that there is no external force in the system, there is only friction and the force that is applied. Since there is no external force, so the momentum, initial momentum of the system will be equal to the momentum of the system just after the collision has taken place, or so just after the block has or the bullet has hit the block. So what was the momentum before the net momentum before the system was formed or the bullet hit the block? The momentum before will be mass of the bullet into velocity of the bullet, which we need to find, plus mass of the block into 0. Why? Before the bullet hit the block was stationary. So before, the total net momentum was m into v, simply because of the movement of the bullet. After the bullet hit the block, what we get? We get that the net mass is m plus m, and the whole system moves with a velocity v. Okay. So by conservation of momentum or law of conservation of momentum, m into v, total momentum before the event took place must be equal to m plus m into capital V, the total momentum after the event has taken place, which will give us small v can be found as m plus small m by small m into v. Now see, we have all the information that we require. Mass of the block is 4 kg, mass of the bullet is 0.01 kg, divided by 0.01 kg mass of the bullet, multiplied by 10 meter per second, right? So 10. Simplify this. This will be equal to 4.0401. 401 into 10, which is equal to 4010 meter per second. So the required velocity of the bullet and the mass system, of the bullet before it hit the block was 4010 meter per second. This is our solution.